Welcome to the fall 2021 version of Earth's Changing Climate. It's a course that I've taught every semester that I've been here at SAIC. It's kind of my original course that I designed. It's what I studied. It's what I know the most about. So I'm going to take you this semester, of course, virtually, on a journey through Earth's climate as it has changed historically and how we expect it to change in the future with global warming and climate change, which is being caused by human activity, right? We'll also spend a bit of time at the beginning of this course talking about the Earth as a system, the different components of the Earth system, the atmosphere, the biosphere, the hydrosphere, and how those all kind of play nicely together. And if we don't understand all of those as a system, then we won't really understand what climate change is, what Earth's climate has been, and how we expect it to change in the future. So, of course, I'm Mika. My office is in McLean 613. It's like a room within a hallway, within a hallway, within another hallway. But I will be there this semester in person for office hours on Wednesday afternoons and Friday mornings if you'd like to pop in and say hello. This is going to be a really quick introductory lecture today. Just kind of whet your palate a little bit about what we're going to be talking about in this course and kind of get the ball rolling as we start talking about Earth's climate. So I'd like to just kind of flash through a couple images of climate change in the news. This, of course, is an iconic image that was taken when massive fires on the West Coast blanketed the city of San Francisco in smoke so thick that it turned the sun orange. So this is an iconic image. You can see the old Victorian homes, right? You can see the downtown San Francisco in the background, and everything is really eerie and apocalyptic. There's no filters on this. This is literally just daytime with the fires blotting out the sun, right? So this, of course, sparked a lot of conversation in the media, on social media, among friends, and especially if you're living on the West Coast, about what climate change means, like where it came from, why humans are causing it, and how we expect it to kind of continue to cause problems and extreme events like this in the future. Speaking of extreme events, another recent extreme event, of course, was Hurricane Harvey, inundating parts of Houston, Texas with over 40 inches of rain. Here's a scene from one of the main boulevards in Houston, just completely flooded from Hurricane Harvey. Estimates are that Harvey was between 20 and 40% more rainy due to extra moisture in the air caused by human-caused climate change, right? As we call it, anthropogenic climate change. Anthropogenic meaning, of course, caused by humans. So anthropogenic climate change caused Hurricane Harvey to be, significantly stronger, significantly wetter, and of course this caused massive flooding problems for the city of Houston. Like a 1 in 1,000, 1 in 10,000 year flooding event, which scientists now say is more common due to climate change. Last summer, 2020, in Chicago was the hottest summer on record, by 0.3 degrees hotter Fahrenheit than the previous hottest summer, which was 70 years ago almost, in 1955, right? So you can see here's a list of the hottest summers. Also in the top 5 is 2012, which was the last time that Chicago saw a 100-degree reading, which are quite rare in Chicago, due to a number of factors, which we can definitely talk about. But 2020 was actually warmer due to warmer nighttime temperatures. And so this is something that we do also expect to happen as we kind of move into a climate changed world, right? We expect nighttime temperatures to be significantly warmer, and this, as you can see from last summer, raises the average and gives us potentially our hottest summer on record. This is, of course, the hottest summer since official temperature records began all the way back in 1871. Oftentimes when we talk about climate change, we refer to graphs that look like this. This is a graph of the temperature anomaly for the globe. This is the global average temperature. If you take every point on the Earth, right? Record the temperature for a year, and then average it all together to get a globally averaged temperature, okay? And then subtract out what we think the baseline or the normal climate should or could be, right? And that's, of course, a subjective judgment call. In this graph, the baseline is taken to be the average temperature between 1951 and 1980. So you can see, where's 1951? Probably right about here, 1980 here. So this becomes the zero line, right? If you were to take all these years, add them up together, average them, divide by 30, you get a temperature that is what we're calling the baseline, and then we take every other year's temperature, subtract it from that baseline to see how far above or below, right, that baseline the temperature has is, or where the trend is going, has become, right? And so you can see that since 1880, the temperature of the globe has risen. Let me just get me out of the way of this axis here. The temperature has risen about 1.2 or between 1 and 1.2 degrees Celsius since 1880 through 2020, right? So that's quite significant. 1 degree Celsius is 1.8 degrees Fahrenheit, so we're looking at about 2 degrees Fahrenheit of warming globally average. Now, of course, that's a very kind of difficult value to kind of understand, right? What does 1 degree of warming mean? How does that translate into my everyday life, my everyday experience of the climate, of the world, of the weather, of the ecosystems around me? So we're going to talk about that quite a bit in this class, right? But this is a figure that's shown a lot. This is a graph that's shown a lot to kind of represent and illustrate global warming or global climate change, right? And it's quite ubiquitous. You've seen it, I'm sure, in a number of different kind of ways, represented differently. This one in particular is showing 5 different unique temperature records, different ways that scientists have compiled and averaged the global temperature. You can see they all agree pretty much through the time series, and they all show this 1 to 1.2 or so degrees Celsius of warming. Of course, the warming isn't distributed evenly across the globe, right? So here's that same trend. Remember that 1 degree of warming number, right? Here's what that trend looks like spatially. So 1 degree of warming globally would be right here, 1 degree. So between the lighter orange and kind of the true orange here. So that's about 1 degree of warming, okay? Which is what this graph showed is happening for across the globe. But what you'll notice is it's not evenly distributed. In the North Pole, for example, we've observed about 4 to 4.8 to almost 5 degrees of warming, right? Just between 1970 and 2019, okay? So it's quite significant. However, here, closer to the Southern Ocean, the tip of South America, we've actually seen some cooling since 1970. Primarily due to sea ice melting, right? And as that cold ice melts into the water, into the ocean, it causes the ocean to be less salty, a little bit cooler. This changes the circulation of the ocean, the dynamics of the ocean. And so it's not an evenly distributed degree of warming. It's not evenly distributed 1 degree everywhere, right? In some places, it's a lot warmer, and in some places, or it's a lot higher, it's a lot larger of a warming trend. And then in some cases, it's a much smaller warming trend or even a slight cooling trend. This is again since 1970. Since 1900, I think the whole entire globe has warmed. What you'll also notice is that, and it's a little bit hard to see because of the scale, if I kind of created a slightly higher resolution scale, you might see this better, but the continents, right, are warming faster than the oceans. So the continents here, for example, North America, you can see it's warming significantly faster than the ocean around it. Now, most people, unless you're Kevin Costner in Waterworld, live on continents. So we are experiencing more global warming than, for example, people who live in the ocean, which is, no one lives in the ocean, but there are islands, right, for example, Hawaii and others, where the global warming has been a little bit less due to them not being on a continent. All right, so that's climate change in the news, right? Those are kind of the buzzy photos and graphs that you'll see a lot of in the news, kind of giving you an example of what we're going to talk about in this class, we're also going to talk quite significantly about the Earth system, the Earth as a system. We're going to talk about how different components of the Earth system play nicely with each other to create a habitable globe, and how climate change affecting one of those components affects all of those components, right? Which is why we call it climate change, okay? And not just increasing temperatures, right? Because the whole climate is changing. So there are four components, to the Earth system, traditional components. There's all of the rocks, all of the magma, the crust, all of that. That's the geosphere, and that's typically studied by geologists. Okay, geologists they study rocks, they study volcanoes and earthquakes. We're not going to talk too much in this class about the geosphere. It does interplay with the climate system, but not as much, and I'm also not a trained geologist, so we're not going to talk a lot about volcanoes. We're not going to talk a lot about earthquakes, although we will touch on them a little bit, as you'll see. The second component, which is what we are going to start with next week talking about, is the hydrosphere. The hydrosphere is all of the water, all of the ice, all of the both liquid, gas, and frozen water on the planet. Okay, so we're talking oceans, rivers, lakes, glaciers, ice sheets, sea ice, and even water vapor and moisture in the air. Okay. The third component of the Earth system, the third sphere, if you will, is everything that's alive. All the plants, all the animals, all the bacteria, all of the microbes, humans, everything that's alive, we call that the biosphere. Okay? And we're going to talk quite significantly about the biosphere and how the biosphere is changing due to climate change and how those changes influence, for example, the hydrosphere and other components of the Earth's climate system. The fourth component of which is the atmosphere. That's everything that's in the sky, right? All of the stuff that's the gas and everything that happens within that gas that's surrounding the solid Earth is what we call the atmosphere, right? So it's like what you see outside, all the cool stuff in the sky. The sun, before it gets to us on the surface, has to go through the atmosphere, and lots of things happen. There's lots of stuff going on in the atmosphere that's kind of interacting with all of these other different components. So changes to the biosphere obviously affect the atmosphere. Changes to the hydrosphere obviously affect the atmosphere. And then, of course, changes in the atmosphere obviously affect the biosphere and the hydrosphere, so on and so forth. Here are some examples of how these different spheres kind of play with each other, right? So here we've got what looks like a thunderstorm, but is actually a large volcanic eruption, sending a lot of different stuff out from the geosphere into the atmosphere, causing lightning and clouds and perhaps some fog, right? And other things. So this is playing between the geosphere and the atmosphere, a little bit of the hydrosphere, because that fog and those clouds are, of course, contain some liquid water, right? Here's an example of that, right? Different components of the hydrosphere. You have ice in water. You've got the atmosphere with clouds in it. Clouds are kind of technically hydrosphere, but they're kind of a mix between hydrosphere and atmosphere, right? So lots of things change as ice melts, for example. That affects climate, that affects the atmosphere, which ultimately will affect the biosphere, right? So here's the biosphere interacting with the hydrosphere. So you got the biosphere, the forest, the trees, all that, interacting with the hydrosphere, the clouds, the fog, which are, of course, in the atmosphere. So all of these things play together, right? There's a big interplay between all of the different components, all the different spheres of the Earth system. So in order to understand climate change and Earth's climate, we need to understand the Earth system first. So we're going to spend a couple weeks at the beginning of the semester talking about these different components of the Earth system, and then we're going to move from that into a discussion of climate change, both historical and future. I also want to talk a bit about the scientific method and plug my own research just a little bit. So So typically, right, the scientific method, which isn't really a method in so much as it's kind of a simplified way of describing how science is conducted, how scientific knowledge is created. So you have the simplified scientific method diagram here, and this is a diagram from a paper that I recently actually just published. So the scientific method will typically start with some sort of hypothesizing, where you're conducting preliminary research and you're formulating questions about some large-scale problem that you'd like to find the answer to. Then you experiment, you design and implement and conduct investigations, you collect data, you do maybe computer simulations, or you go out in the field and you measure soil moisture, or you measure the size of trees or carbon emissions or whatever have you. And then you analyze all those data, right? So you confirm or you deny your hypothesis, you discuss your results, and then ultimately you publish it, right? Or you give a presentation about it and you have some conclusions about your work. And maybe those conclusions are a new theory or a new thesis, or maybe they're just you've solved one tiny little question, one part of a larger scientific knowledge production process, right? And so this is typically how the scientific method is created. The more you repeat these steps, right, and come to the same or similar conclusions, the more robust those conclusions become. So we're at the point with climate change where we have a fairly robust understanding of what climate change is and what's causing it and what future climate changes will look like, okay? But I argue in my research, right, that we can always improve on the scientific method, we can improve on the way that scientific knowledge is created, and then I specifically talk about how we can incorporate methodologies from art and design processes to improve on the scientific method. So where the commonalities between the design process and the scientific method lie are in these steps here, right? So you can see that in the design process, you're ideating, you're prototyping, you're refining, and you're materializing, which are analogous to hypothesizing, experimenting, analyzing, and concluding. But what the design and art-making processes include that the scientific method doesn't really include is this understanding phase, where you're empathizing, you're listening, and you're learning from stakeholders, from actually people who are affected by the knowledge that you are about to produce or investigate or embark on, right? The project that you're about to embark on. And so I think that scientists would be well served if we incorporated some of this understanding phase into our scientific knowledge production. I think that this would probably improve the robustness of our results and also make our results more communicable, more understandable, less abstruse for the general public, who we have to both convince and then persuade to do something about climate change, right? I want to give a little bit of an example of how the scientific method works, and I want to use it specifically to illustrate how I, Mika Tasca, personally was persuaded that climate change is real and is being caused by humans. So let's start with an example, right? So we have our hypothesis, or our observations and our hypothesis, which is that the average temperature of the Earth has been getting hotter. We've observed this, right? And so our hypothesis is that natural changes are responsible. So we're going to say humans have nothing to do with it. Natural changes are responsible for the rise in temperatures that we've observed. So your average run-of-the-mill Republican believes this, right? They believe that, or many of them believe that climate change is being caused by natural variabilities, right? For example, solar activity or volcanic eruptions. So the way we'll test this is we'll compare our observations of the global temperature record with climate models, which are computer simulations, right, of the climate. So we can represent the whole Earth, the whole climate, using equations in a computer model. And let's say that in that computer model, we only include changes that are natural, right, that are caused by the sun, the volcanoes, plants, etc., only natural changes. And what we'd see is that when we run those models, those computer models, we get the temperature record, the global average temperature record looks like this blue line. But the black line here is actually what we've observed. This is what we've observed using thermometers, right? The global average temperature. So the blue line, you can see, does not match the observations. So our hypothesis then is wrong, right? we cannot say that climate change is caused only by natural changes, because when we do that, when we test the hypothesis, we don't get a robust result. We don't get a result that shows that the natural changes to the climate, right, cause a temperature rise as steep and pronounced as the one that we've seen. So we need another hypothesis. We have to go back to the drawing board, redo the scientific method. This time, let's do it with those same computer models, but instead of just natural changes, we're also including human-induced changes. Specifically, we're including human-emitted atmospheric carbon dioxide and changes to land use, meaning deforestation and farming. And we're also going to include in this test, right, and in this hypothesis, natural changes as well, okay? So our observation is still the same. Our hypothesis has changed now, so instead now we're saying that human-induced changes as well as natural changes are responsible. So we're going to run the test again with our climate models, our computer models that now include human-induced changes, and what we get is, let me move myself out of the way here, this graph on the top, okay, so again the black line is the observed temperature rise. The red now is what those computer models of the climate system are saying when we include both natural and anthropogenic or human-induced changes or forcings, right? Again, to remind you, this is what it looks like when we only include natural things. Here's what happens when we include human things. So what I can say from this as a scientist is that this looks a lot better than this. So let's accept then, based on this study, our hypothesis that human-induced changes as well as natural changes are in fact responsible for climate change. This is now the best hypothesis we have so far. We continue to gather data, and find new ways to test and try out this hypothesis. And the more times we get this result, right, looking at this problem from different angles, using different methodologies, using different, ways of observing and analyzing, the more times we get this result versus this result, the more confident we become that this hypothesis is in fact a theory. Or, if you want to go one step further, a principle, right? The more often you observe the same thing, the more confident you can be to say that that thing is actually happening. So this is how the scientific method works, and this is how it convinced me personally, Mika Tasca, that climate change is being caused by both by human-induced changes, by anthropogenic forcings, and that only happens if we include both the natural and the anthropogenic forcings into our climate models. So that's the end of this slideshow for today. Obviously, we've got a lot more in store for you to come. Next week, we're going to talk about the hydrosphere, and then we're going to talk about the biosphere, the atmosphere, and then we'll move right into historical climate change, how we observe climate change, and then what we think the climate is going to look like as we go into the future, namely in the next 100 or so years. So, thanks.